All right, good afternoon, everybody, and thanks for turning up for the first of the New Year talks. We get to talk about a topic that I know that the persona development team has been talking about for a little bit, and we're happy to have Andrew Gallo back from George Washington University to talk a little bit about his experiences. But he's going to be talking a little bit about the use of PTP as an alternative to NTP for perfSONAR measurements. So I will turn it over to you, Andrew.
Thank you. And yeah, welcome to the first talk of the year. Um, this is an expanded version of a lightning talk I gave at the TechX last week in Boston. So this may be familiar to some of you. And I think I've talked in this forum about this a couple of years ago, but the difference with this talk is I've got quantitative results and hopefully an encouragement on possible future use of PTP, this perfSONAR. Um, so the title goes by a couple of different, or the presentation goes by a couple of different titles. I mean, it's primarily dealing with measurement of one-way latency, specifically for nodes that are close to each other topologically. Let's see. There we go. I'll go over the problem statement and let you know how I got pulled into this, what ended up being multi-year project, even if it didn't take me that long to do the work, just took a while to get the results. Uh, because we've got a little bit more time, no pun intended, I'll go over a little bit of some of the history of time and time distribution because I think it's kind of interesting. Talk about time distribution in computer networks, and then I'll go over the test setup and the results. I will talk a little bit about the details of PTP, but not necessarily a full explanation of all the different ways PTP can be deployed. But hopefully we can have a discussion on that. If you have any questions, drop them in the chat, interrupt me, keep them to the end. I'm game for any format that makes you comfortable. So the problem statement. This one I'll read word for word. Measuring one-way latency between two nodes that are geographically nearby can result in negative latencies because the measurements are within the acceptable error range of existing synchronization systems. Clearly, we know that negative latencies are not possible, or even zero latencies are not possible. So a better synchronization strategy is necessary. I see James Deaton joined. I appreciate that because it was on an NTAC call probably going back 2 years ago that he brought up he was seeing this behavior. We got into a little bit of a tangent and a rabbit hole on whether or not PTP was a better option. And we were politely and gently said, why don't you go guys figure that out and let us get back to the regular NTAC business. And so that's what I did. It's been a lot of fun and I've learned a lot about this. So I kind of appreciate being pushed in that direction. So the history of timekeeping. For most of human history, everything was through naked eye observations of the natural world, primarily what was going on in the sky, the sun cycle, the moon cycle, the motions of the stars. Sundial is a very common and obvious instrument to do this, and it provided enough accuracy for the use case at the time. That went up through probably the late ancient to early Middle Age period, in which case mechanical clocks started to come into use. This is a clock from a church in the UK that I think is still operational. Um, but time in this case is still a local phenomenon. It's displayed on a church tower and disseminated through bells, essentially. So if you're in visual or audible range of this device, you knew what time it was. And if you're in another town, you kept a different time scale, or not time scale, but you had different time. The big push, and we'll see this throughout history if you go into a deeper dive, the development of technology really pushed the development of more precise and accurate time. And this is a chronometer developed by John Harrison for the longitude challenge issued by the British Crown or Parliament to develop an accurate timepiece for navigation purposes. And so essentially, the farther and faster we traveled, the more important it was to keep accurate time. So this is a development that reflects the needs of the society at the time. And what we have today in the late 1800s, early 1900s, we have electrification and pocket watches. So electrification allowed electric clocks, and the pocket watches really democratized and made timepieces cheaply available to the population as a whole. And dissemination of that time was pretty easy with the electric system. So what do you got? And in the atomic age, which started in the mid 20th century, we started using the behavior of atoms to use as a timekeeping, not necessarily timekeeping, but a frequency keeping standard. Again, as communications and technology needs improved, so did the needs of timekeeping, and the precision and accuracy keeps getting more and more, well, precise. So again, throughout human history, information and people really didn't travel faster than biology. I mean, the fastest you could move information was by horse. I mean, there may have been some cases where there were optical distribution systems, such as the was it the optical telegraph in France that was used, but that was a very specific and narrow use case. So it wasn't necessary to coordinate time between and among different communities. So let's see. Again, this is time distribution through visual means. This is the famous Greenwich Observatory with the ball that would drop at noon every day so that ships in the Thames River could adjust their chronometers to match a noon exactly. This is probably my favorite part of doing this research. This is Ruth Belville. In her hand, she has a very accurate pocket watch. And once a week, she would go to the observatory and have it set by the observers. And she would walk around London and sell time to various organizations, can think jewelers, financial institutions, who needed accurate time. So what we see is Ruth is essentially human biological NTP in the Victorian era. She did this well into her old age, and this is how she made a living. One of the more interesting ways to distribute time in France, and I think Austria as well, there was a pneumatic system to set clocks so that there were pipes underground that carried air pressure to various municipal clocks to keep them in sync. What I find interesting is there are various new technologies that were tried out. And in the mid 1800s, the pneumatic technology was quite popular and used for many things. Some of you, if you're old enough, may remember the tube. Well, they're still used in banks and pharmacies, the pneumatic tubes to move primarily small pieces around. Was used in New York for the post office. There were some proposals to even use it for funeral transportation, which just blew my mind. I could not find any examples of this, but I did what anybody would do in the last year, and if you can't find an example of it, ask a generative AI to make something for you. And so this is what two examples or three examples of pneumatic funeral transportation that ChatGPT thinks could exist. I think I like the steampunk and Mad Max motif of this one. So time distribution in computer networks. For most of our history, and what I mean by that is, most of us have been doing this for a number of years, but even going back farther than that, it's still been NTP, or the Network Time Protocol. An NTP is a classic end-to-end internet application, and this is important for comparison with PTP. What I mean by a classic end-to-end internet application is that it is a client and server setup. The client asks several NTP time servers or NTP servers for time. The intermediate networking elements know nothing about the UDP packets and the Ethernet frames they're moving around. I suppose you could configure quality of service to match and treat NTP packets differently. I've never seen or heard of examples of that. So essentially, the switches and routers between the server and the client just treat it like all other traffic. The NTP client uses algorithms, and I put that in quotation mark and parenthetically saying possibly only understood by David Mills, because this stuff gets pretty complicated pretty quickly. But using those algorithms, the client selects the best source for time and then keeps its system clock in sync with the selected server. The performance of NTP varies widely. In what I'll call well-behaved campus networks, which most of us run, you can achieve accuracy on the order of 1 to 10 milliseconds of agreement between the requesting host and the server. And what I mean by well-behaved is networks that are not congested and don't tend to have a lot of drop traffic or high jitter. If you're querying time servers on the open internet, that tends to make the performance a little worse, and you could see accuracy on the order of tens to hundreds of milliseconds. But considering that NTP is usually configured once, if at all, because it could be automatic through DHCP or through whatever operating system is installed, that accuracy is pretty good for what's essentially an invisible process. This is good enough for time of day synchronization, which is important for authentication. It's generally good enough for log time stamping, event correlation, automation tools such as cron. You generally don't need millisecond level accuracy, but you can achieve it. But is NTP good enough? The convergence of other technologies to IP over Ethernet demands better synchronization. And specifically, I'm thinking of cellular communications in this case. In many of our early careers, there was the battle between the TDM network and IP over Ethernet. Well, IP over Ethernet won. T1s and SONET technology is now deprecated and rarely seen. But the benefit of those previous technologies were that they used domain-specific features that inherently provided synchronization. I mean, after all, T1s and SONET were time division multiplex networks, so you could easily and natively and naturally derive time and frequency, or at least frequency and phase synchronization from those underlying transport technologies. As we move certainly from 3G to 4G, but especially 4G to 5G for cellular, we have very strict timing requirements at the radios. The radios need single-digit microseconds, which is 2 orders better than what we discussed in the previous slide, 2 orders of magnitude better performance than NTP. That's needed to keep the radios in sync for roaming. So when clients roam from one radio to another, that level of time synchronization is important to provide a good quality of service. So as cellular backhaul has moved from T1s to SONET to IP over Ethernet, the carriers needed a way to derive and share and distribute time, specifically frequency and phase synchronization. And there's the option of putting GPS at every cell site, which might be possible if you're still running macro cells only. But with 5G, which is often deployed with a lot of small cells, that's just not feasible. It becomes too expensive. There are a couple of other canonical examples of the need for better than NTP timing. High frequency trading is one of them. There are regulatory requirements to keep records that require sub-millisecond timing. And so you need something better than NTP for that. Audio video bridging often uses precise timing. I was surprised when I started working with some of the campus engineers on Crestron devices. If some of you may be familiar with those, they're used in classrooms for video streaming and content streaming and audio. The Crestron source, there are encoders and decoders, and they will form their own little PTP network and keep themselves perfectly in sync. And that allows for audio and video to stay synchronized, as well as all the displays to affect a scene change at exactly the same time, which is kind of cool. The power industry is also using PTP to ensure that the grid stays stable and synchronized to, in this country or in this continent, 60 cycles per second. But our focus here is not going to be on any of those needs. It's going to be on measuring the latency of machines that tend to be very close together. So most of us are familiar with perfSONAR. It's deployed to run tests between and among campuses and run a variety of tests such as throughput, latency, and traceroute, both scheduled and on demand. And what some organizations have seen is this is really cool. We want to run this on our own campus, in which case you're now running multiple perfSONAR nodes in a very small geographic area and have low latencies. And again, what was found by several people I've talked to is that they were seeing negative latencies because, again, when the latencies within the range of NTP's acceptable error range or performance objectives, your resolution doesn't match up with what your needs are. So let's go over some really basics here, just to level set everybody. When you measure latency, ping is obviously the common thing everybody goes to. It's a single-ended test that doesn't require coordination of the far end. It's almost always enabled and working unless you're talking about an intermediate box like a firewall that's filtering it. The requesting station sends out an echo reply. It is received by the end host or the far end, and I'm sorry, the original test station sends out an echo request. The reply is received and sent back. The far end receives the request and sends the reply back, and the original test host then compares the outgoing timestamp with the replies timestamp and can calculate what the round trip time is. Because only one host is involved in keeping time, there is only one clock, and therefore it's really easy to keep things in sync. Specifically, what I mean is the amount of time it takes for even in a troubleshooting scenario with even high latency, the one host's clock is not going to drift enough to affect the RTT measurement. Their round trip time is the sum of two one-way latencies, the forward and return path, but the RTT can hide both path asymmetries, meaning both topologically and in terms of performance, which is why we do one-way latency measurements. So how do you do a one-way latency measurement? Well, it's a dual-ended test, and both sides need to coordinate and agree to be part of this test. The sender sends out a packet with an included timestamp. The receiver or far end receives the packet and subtracts the two timestamps and sends the report back to the originator in order to inform it what the one-way latency is. We now have two clocks involved and two timestamps, and that's where we run into a problem. Probably the most common program everyone uses is OWAMP to do this. So when the nodes are close together, you can have those clocks be in such a situation that negative latencies result. So again, just as a way to repeat, NTP provides good timing performance in an easy to deploy application. single-digit millisecond accuracy, and private networks, which is what most of us are running. So, what are some of the solutions to the negative latency problem? Well, you could tune your NTP configuration. You could run your own Stratum 1 server, which is fairly easy and inexpensive to do. You could make sure that the nodes are not far enough, the NTP servers are not far enough, are not far from the nodes that are involved in the test situation or the test setup. This still isn't good enough, and I can demonstrate that. You could use cronid, which is a replacement for NTPD. Cronid uses the same on-the-wire protocol. It's still using NTP packets, but is generally considered a better performance and better timekeeping tool. I haven't done any NTP versus cronid tests, but some of the documentation and some of the forums I've read do indicate that cronid is better than NTP at keeping a system's clock in sync. I think it's more for cases where devices are intermittently connected to the internet and do better. It does better than NTP, but that doesn't really come into play in our situation. The third option is what we'll discuss here is using IEEE 1588, the precision timing protocol. So, how does PTP differ from NTP? Well, routers and switches are violent places, and they do violence to NTP packets. We've got queuing, buffering, reordering, switching, routing, packets get dropped. And these things not only delay packets, but they do so in a way that is variable and unpredictable. And that interferes dramatically with trying to keep clocks in sync. So, what's a classic NTP setup? Well, time almost always comes from the GPS satellites or other satellite-based navigation systems, generically referred to as GNSS. You have an NTP server, which is Stratum 1 because it is at the top of the hierarchy. The NTP server will start emitting packets in response to requests out onto the internet or into your enterprise network. We all think we know what goes on inside our networks, but like I said, networks do violent things to NTP packets, and the client receives the NTP packet and will become a Stratum 2, 3, or 4, depending on the number of NTP servers that these packets go through. PTP, there are a number of features of PTP that allow it to be better performance than NTP. The first is that it is generally deployed in much smaller installations. You're not running a continental scale PTP domain with the 1 or 2 grandmasters, so it tends to be either geographically based or site or campus based. The primary way is the second bullet point. It's hardware assisted. All the networking elements between the master and slave need to be, and I put parenthetically should be, but they need to be PTP aware. And what this does is this allows for the networking elements to account for and update the timing of the packets for queuing, switching, and buffering delays. PTP also tends to have higher polling intervals. So instead of once every several seconds to several minutes to hours that NTP uses, PTP is on a couple of orders of magnitude more frequent, that it is usually several to tens per second. So what does a PTP distribution look like? Again, using the previous frames format. We still start with the GPS satellite as a source of time. There's a PTP grandmaster, which sits at the top of the hierarchy. So what I'm showing here is a detail of a specific and generic networking element. This could be a switch or a router. As soon as is possible for the networking element to identify that the incoming frame is a PTP frame, it will timestamp that frame and treat it like other traffic. And then on egress, look at the timestamp and update how much time that frame has spent transiting through this specific networking element. There are a couple of different, well, there are many different ways to deploy NTP, or I'm sorry, PTP. Two broad categories are transparent mode and boundary mode. What I'm showing here is transparent mode. So think of a frame going through a switch. When the switch receives that frame, it as soon as it recognizes it's a PTP frame, it starts doing the hardware timestamping. And then the PTP slave receives that and accepts that as the time. So this is a diagram of the topology I was using for the testing I was running. At the bottom, I've got a pair of Dell R630s running perfSONAR and running one-way latency tests between them. The distance between them, the fiber distance between the nodes is approximately 1 kilometer. Each node is connected to a single upstream switch that is acting in boundary mode. We'll talk a little bit about that later if we've got time. And then each of those is connected to the same Juniper MX480. So topologically, it's very simple. They're close by, and it's also a very stable setup. Each of those switches has a direct connection to a PTP grandmaster, two different grandmasters in this case. And also, for purposes of NTP, the device on the upper right side, the Meinberg M1000, is the campus NTP server that I used for NTP testing. The nodes did have to go through the campus firewall and a router and one switch to get there, but still fairly topologically close by for NTP. I ran 4 different test scenarios. First one is using PTP, specifically PTP for Linux. I did 3 different NTP cases. And the first one was NTP best case, which used that campus Stratum 1 server with the shortest polling interval I could configure without special configurations on the NTP server. And that resulted in a polling interval of 8 seconds. If I tried to go shorter than 8 seconds, the server just silently ignored the requests. So I figured once every 8 seconds was a common number that people might try. The NTP typical case is using publicly available, or at least available to this community, NTP servers on the Internet 2 network. Previous versions of perfSONAR had a button you could click that would auto-configure multiple NTP servers. Don't think the newer versions do, but I had some older installations of that where I could just grab the servers and use those. The NTP worst case, I found 2 Antipodean public NTP servers that were reachable only over the commercial internet. And I set the polling interval to be fairly long. I think it ended up being 1,024 seconds. I think the servers I ended up using, one was in New Caledonia and one was East Africa, maybe. So what is PTP for Linux? It's a collection of tools. The PTP for L implements the IEEE 1588 protocol. The PHC to sys is what synchronizes the system clock to the PTP hardware clock. What's interesting is when you start digging into this, you realize that there are a lot of clocks in a Linux system. And when you're running PTP, what happens is you can synchronize the NIC clock to your PTP upstream, but unless you're using these sets of tools, the system clock won't be. So the PHC to sys is what handles that. TimeMaster manages all of this for you, which is pretty convenient. What it does is it will launch PTP for Linux, the PHC to sys, and either NTP or cronid. And this is great because it allows for fallback to NTP in case PTP is either unavailable or unstable. And the way this works, or the way the key here for when PTP is working as it should, is the NIC. Again, PTP gets its benefits from the everything being done in hardware, so the NIC will synchronize to the upstream master. And then there's a shared memory driver that essentially makes the NIC clock look like an NTP server. And then the either NTPD or cronid will query that clock once every 8 seconds. There's also a management client where you can query both the local software and some of the various components in the network, such as your upstreams, to get information from them. All right, so I used cronid. I collected a whole bunch of statistics. I won't go over all of these. cronid provides a lot of interesting information on what's going on. I will do have some graphonographs showing, I believe, showing some of this behavior. So what are the findings? Well, results get worse with less ideal configurations. I deserve a prize for that. So I essentially proved the obvious. PTP performs much better than NTP. There are no surprises there. What I found interesting is even under the best case NTP scenario, I still saw negative latencies. That was a bit of a surprise. Again, going back to the negative latencies comment, obviously we know that latency can't be negative, but it really should be something greater than 0. So when I was doing my analysis, I wanted to make sure that I wasn't just looking at negative latencies, but really anything that was below a realistic threshold, because it does take some time to get packets through a switch, a router, another switch, and 1,000 meters of fiber. But I ran into a chicken and egg problem, and that is, how do I measure that latency when I'm testing the programs I would normally use to measure those values. So what I did was I sent 1,000,000 ICMP packets between the hosts, 500,000 originating from each host with ping. Out of 1,000,000, the absolute single lowest value I got was 0.4 milliseconds. And that was exactly 1 frame out of 1,000,000. That is realistic given the fiber lengths and the networking elements the traffic was passing through. I divided that in half for a one-way latency. And just to give myself some headroom, I cut that in half and used a threshold of 0.016 milliseconds. So any packet that was less than that value was considered impossible and invalid. Some graphs in Excel on what we saw. So a little bit of detail on the perfSONAR results. The test run once a minute, and I think it's 100 packets in each test. And each of those is a run. So the graph on the left is the number of runs with at least 1 packet below the threshold. PTP had none. The NTP best case had just under 3,000 test runs out of 10,000 that showed negative latency. And the reason there's a reason I use 10,000 tests as my sample size. Those are the most results you can get out of the API at any one time. So rather than try and put them all together, I just used the maximum the API would give me, and it was very close to 7 days. So I was able to run essentially 1 week tests. So that's what these graphs represent. So in the course of 1 week, the NTP best case had about 2,500 runs where one of the packets had latency below the threshold, and it gets worse from there. The graph on the right shows the minimum and maximum latencies of each testing scenario. Again, PTP had no cases of below threshold values. The NTP best case did. The default case is much worse. And I didn't even include the worst case because it would dwarf the other two so much that the graphs would be just at the zero line. So here are some graphonographs of the latency. The top graph is the PTP, the test running under PTP, and shows a range of 0.04 milliseconds to 0.1 millisecond. You see it's also very stable with very little variation. The graph below that is the NTP best case, and the range is from negative 0.2 milliseconds to plus 0.3 milliseconds. You'll also see that there's more variation in the results. These two graphs are for the next two test scenarios, the default case and the worst case. And again, you'll see that the ranges vary, increase from negative 1.5 to 1 millisecond. And again, much more variation. And the worst case is just all over the place. I mean, there were some test runs where I was getting 40 milliseconds between these two nodes, and they were within 5-minute walking distance of each other. So, what are some other analysis and continuing work I'd like to do or see others do or help with? I'd like to look at what the jitter or other. I'd like to do an analysis of jitter relative to other metrics such as server temperature, because that's one of the biggest impacts on oscillator performance. I'd like to correlate the time series data that OWAMP provides with the time series data that cronny-D provides, because cronny-D, as I showed you before, provides a whole bunch of statistics which might have some interesting correlations pop out of. I'd also like to generate a map, a geographic map that's also a heat map of where PTP is needed. And essentially, I've started collecting some data on this. Essentially, what I did was I used the RIPE Atlas to send a lot of ICMP traffic towards our network and collected those latencies. So what I'd like to do is essentially build a map of concentric circles and say, if I can get NTP to be within plus or minus 5 milliseconds, then within this circle, anything we see, we can't use NTP as the synchronization technology because the results are not going to be good enough. I've talked to Tim from the UK. I believe some of you may know him. I don't think he's going to be able to make this call. And he mentioned that they're running some perfSONAR nodes in metropolitan London, and they are running into this problem as well. They have considered or are looking at PTP, and so we're going to be talking a little bit more in depth on what I found. So some deployment considerations. We'll talk a little bit about PTP here. For as much as I want to encourage folks to consider and potentially use it, PTP is not a drop-in replacement for NTP. As I mentioned before, the primary benefits of PTP are accrued because of the hardware assistance of each of the intermediate elements and the end nodes. So you have to make sure all your intermediate devices support PTP. You have to keep the topology of the network in consideration in ways that NTP just doesn't care about. You also have to be careful about capacity. Our NTP servers can, I think I calculated, handle up to 1,000 clients or 100,000 NTP clients at common polling intervals, considering a client will usually settle down to once every 15 minutes. But PTP, given that it is on the multiple orders of magnitude more frequently, you'll often see capacity numbers in the hundreds of clients range. And in some cases, that's a licensing thing, but legitimately, it's a hardware thing as well, a hardware constraint as well. that's also where a boundary clock may be appropriate. And essentially the difference between a transparent clock and a boundary clock, you could you could think of it like a switch that is in the same VLAN might be a transparent clock, where the PTP slave and PTP grandmaster are talking directly to each other, whereas a boundary clock is a back-to-back situation where the switcher router itself has a master on one port and a slave on another port, so it regenerates the clock. I ran into some what I think are compatibility problems, or at least having profiles in common. So here's where the details of PTP get really kind of irritating. It started out as being a pure layer 2 Ethernet protocol, which is, I think, how it ended up with the IEEE. I think some folks went to the standards bodies and said, we need better timing. And it was done through the IEEE. In my mind, I consider this the way, or I analogize it with Wi-Fi, and that is the IEEE comes up with the low-level standards and define how the hardware should work. In the Wi-Fi world, the Wi-Fi Business Alliance, I believe it's called, then takes those, packages them together and say, all right, if you want to use our logo and say you're compatible, you need to behave this way using these. Some are required standards and some are optional. Well, PTP did something similar where several organizations and other standards bodies, primarily the industry specific, have created what are called different profiles. So the telecom industry has a profile or multiple profiles. The power industry has a profile. The audio video bridging folks have a profile. I believe the IETF has developed an enterprise profile, which is what we might use. I tried to get an Arista switch and a Juniper MX talking to each other, and I just couldn't figure it out. It's possible that they don't have profiles in common. I didn't go down that far. I did get two Juniper MXs to work together, which shouldn't be too much of a surprise, but that was nice to see. But that is certainly something to keep in mind. We I'll go down this rabbit hole a little bit because I want to leave time for questions. I did get sucked down a rabbit hole so far. I mean, I am not a developer or a Linux system admin, but I was using strace one Saturday morning to figure this out. So I was using a Cronny exporter or a Prometheus exporter specifically written for Cronny to collect statistics. And it worked fine when I was using NTP, but it broke when I switched to PTP. And for the life of me, I couldn't figure this out. So what did I eventually find? Well, Cronny and NTP does this as well. It keeps track of its upstreams using a reference ID in order to prevent timing loops. So this is the output of the Cronny client tracking command when it's synced to the PTP clock. The reference ID is a 32-bit hex value, in this case 50, 54, 50, 30. And it is indicating it's a Stratum 1 server. So the definition of the reference ID is a 32-bit value. When it's an IP address, it's just the 32-bit IP address, just represented in hex. If your upstream is an IPv6, you take the 128-bit address, run it through, create an MD5 sum, and take the first 32 bits of the MD5 sum. But that's not what we have in this case. We just have an ASCII value PTP0. The Cronny exporter does a reverse name lookup on the reference ID. So, like I said, a hint, it's always DNS. PTP0 gets converted to hex. The ASCII values of PTP0 gets converted to ASCII, or the ASCII values get converted to hex values of 50, 54, 50, 30, which go or are translated to an IP address of 80, 84, 80, 48. And when you do a reverse name lookup on that, not only does the record not exist, or I assume it doesn't exist, the authoritative name servers just don't even respond. They time out. And so Cronny, or the Cronny exporter, caused Prometheus to time out, and that's that cost me about a couple of hours worth of a Saturday morning trying to figure that out. With that, let's see. I have some slides of um, the data formats, but that's really if we wanted to talk about how to do a deeper analysis. So I'll skip those and then close it up and open for any questions. I will go
All right.
back.
Well, thank you so much for going through all of that. Everybody now has the ability to unmute themselves again. I've already received several Slacks from members of my own organization who have many, many questions and
Uh-oh.
comments that they would like to go over here. So I won't throw anybody under the bus, although it starts with George and it ends with Rob. I know that he has a couple. But let's open it up in case anybody does have any questions or comments. I can start us off with one, just because I'm an old NTP nerd that used to work at Delaware with Dave Mills, and
Wow.
yeah, he was my first boss when I got there in the early 2000s, just doing a small project. But one thing that I remember that he was always an advocate of was keeping costs low. So my question is just going to be, how much did it cost to actually have, the PTP capable devices and stuff like that? And I know that for a large organization, it's not a big deal to have stuff like this. But for a small organization and somebody who's looking just to get started with perfSONAR, what would they be looking at to sort of get all of this up and running from a hardware perspective?
Okay, that's a really good question, and I'm glad you've asked that. And I'm not, so the short answer is you can now do this pretty cheaply. Um, I remember talking about PTP. There was a TechX in Cleveland many years ago. Dan Magorian and I presented on this, and one of the criticisms was PTP is expensive and complicated. Well, it is fairly cheap now. You can go on Amazon and buy a PTP capable, I think it's a time machine for less than $400 or $500. Um, in that case, probably the most expensive and difficult part of your project will be getting GPS cabling to the roof of your building. Once you have that cable in place, then your options can range from a couple $100 to several $1,000s. And again, the time machines you can buy from Amazon is pretty inexpensive. If you want a real do-it-yourself solution to just get your feet wet, you can, for maybe $150, get a GPS hat and Raspberry Pi and have yourself a PTP capable server. The Raspberry Pi 4 and 5 have the right hardware to do PTP timestamping. I've got one at home. Unfortunately, the layout of my apartment means I've got no Ethernet near the window, and you can't do PTP over Wi-Fi. But that cost me maybe $130, maybe a little extra with the case. For a real enterprise deployment, the Symmetricom and the Meinberg are going to be several $1,000s. Again, if you've got the cabling and antenna in place, you're looking at less than $10,000. And these things, the life cycle on these things is quite long. I'd say between 5 and 10 years. So it's a little bit of money, but there are options if you wanted to keep it low cost.
All right.
Well,
Well, thank you.
and it sounds like they're comparable to doing real Stratum 1 NTP server kind of things too.
They absolutely are. In fact, both of them are.
Yeah.
The Meinberg is a card-based, flexible. It's a 1U chassis with some cards. So we've got a 4-port NTP card in there and a 1-port PTP card. And they absolutely do Stratum 1. And if you're really fancy, you can buy high precision rubidium oscillators and have redundancy. So yeah, we went with NTP and PTP combination for the M1000, and I think it cost us maybe $3,500 per piece. You can also get, and I don't want to spend too much time on this. You can also get, I think it's now owned by Adtran. They bought it from Adva. which bought an independent company called Oscilloquartz, which is an SFP form factor PTP and NTP Stratum 1 Grandmaster combination. And then those are less than $1,000 a piece.
All right. So George also put in a link to a card inside of the chat if people are interested in that. Michael, your hand is up.
Yes, do most of these appliances for PTP support the entire GNSS constellation set of constellations, or are they tunable to just GPS or Galileo or GLONASS or whatever?
That is very hardware specific. When we bought the Meinberg, we bought the GPS 180 card, which is just the US constellation, which is more formally called US Navstar. Most of the hardware you buy today is multi-constellation, so it'll do US Navstar, it'll do Europe's Galileo, it'll do the Russian GLONASS, and maybe the Chinese Beidou, I think it's pronounced. And again, depending on your environment, you may even be able to get hardware security for spoofing, which probably is not something that's of interest to this type of installation or implementation or use case. But to go off on a whole tangent that I'm not qualified to speak on, there is a tremendous amount of activity to build better navigation without relying on satellites. This use of the GNSS constellations for time is one of three that is generally referred to as PNT, for position, navigation, and timing. And it, at least in the US, has high visibility as a national security and strategic security concern to maintain PNT capability in a GPS denied environment.
Right. Thank you.
Okay. Christopher, you have your hand up.
Yeah, so did you use the hardware timestamping on your network card when you were using NTP, or and did it make a difference compared to not using hardware timestamping?
For NTP?
Yes, for NTP.
Honestly, the short answer is no, I didn't, because I don't know how to do that. So that's a possible test we could run. This topology is still in place. So maybe you and I could talk and we could run that test.
Yeah, that would be really quite interesting to see whether it makes a difference, or whether it's the transparent clock or boundary clocks that are making the difference.
Yeah, absolutely. I did receive your email earlier. So we'll set up a time to talk. And like I said, this test setup is still in place. So let's use it and do some more tests.
Okay. And a couple of more links have been shared in the chat if people are following along over there on some hardware and other options. Does anybody else have any questions that they would like to ask?
Standard ESNet question. Have you been playing with any of the testing via IPv6 stack and noticed any improvements or performances? And then another one that's lightly related. In your cronny testing, have you attempted to use a ref clock that is to the dev PTP or the fizz on the NIC itself?
The first question about IPv6, when I was trying to get the Arista switch and Juniper MX talking to each other, I tried everything I could, including using IPv4 unicast, IPv6 unicast, multicast. I could not get them to work. When in transparent mode, it didn't really matter. In some cases, I set up some IPv6 stuff, but it didn't really matter. So I haven't been able to. I can't definitively say that there's a performance change based on v4 versus v6. If I'm understanding your second question correctly, I believe the answer to that is yes, the way I set this up, and I can share my cronny configs or PTP for Linux configs, and you can confirm this for me. I believe it did use the shared memory, or I know it used the shared memory driver as a shim to access the hardware clock on the NIC. So I think the proper answer to your question is yes.
Excellent. And if there's not another one, were you doing any specific protocols or just native 1588? Have you looked into like telecom, like the G8275.2 to leapfrog the dependency on every single device participating?
No. However, I don't know if he's on this call. John Simpkins from Michigan came up to me after the TechX talk and raised that question. I believe there's another term for that as partial assist or partial path assist. And what that does is that allows for an incremental deployment of PTP in cases where intermediate hardware does not fully support PTP. I did not try that. As you see in this topology, it was extremely simple, and all the hardware supported it. However, I think if we're going to talk about using this in the community, we may need to look at other profiles that do support that partial path support.
Excellent. Thank you. And fantastic talk. Thank you.
Thank you.
All right. We're near the top of the hour. I'll put out one last call in case anybody has any other questions.
Well, I guess I got a quick one. Is there a quick PTP, PTP for beginners or anything like that would, if somebody wanted to dig into this a little bit?
I think I think it was George or Chris put in the chat. Red Hat has a really good guide to do this. That's what I used.
Okay.
It's fairly straightforward. What I would hope from this talk, and I got quantitative results here, and I wanted to share them with the community because I know some people have seen this problem. But what's not odd, but I don't really have that much depth in PTP. What you see is the topology I know how to make work.
Yeah.
Like I said, John Simpkins from the University of Michigan has been doing some testing on some newer profiles. And Tim and Chris from the UK have more experience with this than I do. And the Europeans in general are probably more advanced than we are in the US when it comes to time and frequency distribution. What I'm hoping is that we build a little bit of community knowledge and share that with each other. So I'd be happy to jump on a call with anybody, and maybe we can set up, not necessarily in this format, but a little bit more of a working session where I could get into the hosts, show you the config, show you the behavior, show you some of the command output of the Arista switches and what's going on, and you guys can start playing with it on campus.
Sounds like you just talked yourself into a talk in this session in a couple of weeks.
Fair enough. Like I don't know if this is the right forum for it and to get into that level of detail, but I'm pretty easy to find, I think. So I see a couple of folks have said they're interested in doing this. So hit me up over email or Slack or however you can get in touch with me, and maybe we'll set up a time where we can all geek out. Without going too far and throwing anybody under the bus, so to speak, there's somebody for Internet 2 who's got not just a PTP grandmaster, but an atomic clock and a rubidium oscillator at her house. So there are timing nerds in this community, and I don't see her on the call. So I won't volunteer her frequency expertise.
Yeah, they're everywhere. All right. Well, thank you again, Andrew. Send me the slides when you can. I'll make sure that those get posted. And we do have a talk again next week. We got a full couple of weeks. Nick Sultana from Illinois Tech is going to be talking about his experiences in network profiling on some of the federated research test beds that are deployed. And then Week after that, we have a residency with Michael Sinatra, and he'll be going over some of his BGP and segment routing findings. Also, a TechX talk that he is revisiting here. So, hope everybody has a good week, and we'll talk to some people next week.
All right. Thank you. Take care.